Okay, we're back. We're going to take a look at these 20-point problems on the test. This is problem pretty much like what was done in a previous video. We've got a rectangular sheet. Dimensions are 20 by 14, but we are to cut out the corners, okay, which are x by x, and then fold it up to make a box, which means this dimension is 20 minus 2x. This inside dimension here is 14 minus 2x, which serve as the length and width. Makes no difference which is which, obviously. 14 minus 2x and 20 minus 2x. Okay, so write an expression for the volume. The volume is length times width times height. The height would be, as we saw in the videos, this would fold up. This is x, so that would be the height. So the function is x times 20 minus 2x times 14 minus 2x. Now, you didn't need to expand that. That's perfectly fine. In order to optimize that, we need to go to the calculator because this is non-quadratic. I believe I have that keyed in here just that way. Okay, so I'm going to come and go look at that. Okay, so we've got that in there. Now, what are the legitimate values of x? Well, you can't cut away more than half of the length of the shortest side. So we're going to look in for values between 0 and 7. So we've got that in. We're going to go to our table set, do the ask, and or no, we'll do the auto. Rather, we will do the auto. Okay, and we'll look between 0 and 7 for the high point. Okay. So we'll set this to begin at 0, increments of 1. We'll establish that, and then we'll come and look at the table. Here's looking at the table now. Okay. Want me to look at the table. Okay. Look at the table of values between 1 and 7. We see that this is peaking out here at about the x value of 3, peaking out at about 336. So that'll give me a gauge on how to set up my window. I'm only going from 0 to 7. I've said I'll go up to about 350, 400, just so I can see the peak of that. Okay, let's go and graph that. Okay, that peak, that's my turning point. That's the value of x producing the highest area. So F5 to find the maximum, and that would be left and right of that, to hone in on it. Okay, there we go, and just to the right of that now, and there that goes with an x value of 2.7. 2.7, okay, that's the size of the cut, 2.7. And then the y value is the maximum volume of 339. So determine the x value for maximum. We said that's x equals 2.7, and the volume is 339. The length is 14 minus twice 2.7, so 14 minus 5.4, whatever that means. I don't even care if you leave it at that. Width is 20 minus, again, 5.4. Okay, that's done. All right, here we go with this, getting the oil in from out to sea. Okay, and it's told to us the oil was discovered 20 miles out. Okay, and 100 miles down shore. So that's setting this up. Okay, we need to find the most expedient way of or the most cost-efficient way of bringing this oil from point A to point C. Okay, so I'm asking you to explore 3 different options. Okay, but then again, the one which is the most cost-effective is what we're after in the long run. Okay, um, so we're saying that offshore to bring it in, to run the pipe underwater rather, is $10,000 per mile. Okay, and to run it across land is $5,000 per mile. They're given, they're my constraints I have to work with. Okay, what I'm going to do is I'm going to presume that there's some optimal location here at D, implying that the length BD is X. Okay. Then the length DC would be 100 minus X. Okay, so now, okay, I'm going to say that my cost is going to be the price per mile along route AD, so that's 10,000. I'm just going to leave it as 10 times the route AD plus, okay, 5,000, and just I'll multiply everything by 1,000, 5 times the route from D to C. Okay, and that's going to be my cost. Now, of course, that's not a cost function because it's not expressed in terms of X. So DC was clearly 100 minus X, and AB is, from the Pythagoras and the right triangulation here, AB is root x squared plus 20 squared, or 20 squared, which is, of course, 400. Okay? So my cost as a function of x is going to equal, okay, 10 times the radical 400 plus x squared, or x squared plus 400, makes no difference, plus 5 times, of course, this is all times 1,000. Okay? So it's C of x, the cost as a function of x, is, clean this up, 10 times the square root of 400 plus x squared plus 5 times 100 minus x. Okay, now I can really just key that in and answer the questions based on the outcome of my calculator. Okay, so I'm going to key that into my calculator, which is already there as y1. So that's in there, okay, right there. So I'm going to have that turned on. And now I'm going to just look at my table with the ask values, okay? So I set my table so that I can put the values in that I want, okay? And then go to my table, and the first value is x equals 0, okay? So putting that in. It looks like I didn't turn that on, so let me toggle that on to the ASK mode. Okay, now that's taken. Okay, so now I'm going to put in 0, and that costs 700,000. Okay, so that's 700,000 there. I can also, this actually I want it as 100. Okay, you put 50, I don't care, because you could just read it off the table. All right, so go back to our calculator. So at 50, my cost was 788,000, and 100, my cost was 1,119,000. So that's what I'm going to put. So the cost of going the route AB to BC is 700,000. 700,000. The cost of going directly from A to C is the cost going directly, that's the most expensive cost because that's totally underwater. So that's at $10,000 per mile underwater. That's going to be quite costly. So that was $1,019 something, I don't know, whatever it was, that's fine, leaving it at that. Now the optimal cost, okay, Again, I need to go to my calculator. We'll take a look at that, find the optimal cost on that. All right, we can see here that 1,000 seems to be the somewhere. I want to be able to go less than 700,000. So I'm going to look upwards to about on my graph about the x values running between 0 and 100, and the y values running up to, let's say, 1,200. Okay, 1,200, 1,500 doesn't really matter much. So let's take a look. Set the window. X running from 0 to 100. Okay. Here we go out to 100. Y running up to, we just run it up to 1,300. Okay. I'm sorry, that's the Y minimum. I want the Y minimum at 0 to Y max at 1,300. Okay. Looking now at the graph. Okay. We should find a low point in here. All right. So F5 for the minimum. Scrolling to the left. Over to the left. Okay. All the way over to the left. Enter, left bound, right bound. This should be covering the low point right about there. Okay, I'm getting 11.5 for $673,000. Okay, so 11.5 miles is the value of X for the minimum cost, which was the cost minimum is $673,000. Okay, savings of what, $27,000 over this route. Okay, so definitely the most cost-efficient way to go. Okay, the last problem here. Last problem says we got this track, 3,000 meters all the way around. Okay, X. All right, radius here. All right, write an expression for the perimeter of the shape in terms of X and Y. Well, the perimeter is 3,000. It's composed of two straightaway lengths of X plus the circumference of the circle, which is 2 pi r, and that's equal to 3,000. Okay, I can divide through by 2, get X plus pi r is equal to 1,500. And from that, write the above expression, solving X in terms of R. X is equal to 1,500 minus pi r. Okay. Next, we're asked to write a function expressing the area. The area is mainly just a circle plus a rectangle. The dimensions of the rectangle, of course, are x by 2r, x by 2r, x by d, and the circle is just pi r squared. So the area formula is pi r squared plus 2rx. Enter this value of x, pi r squared plus 2x times r, which is 1,500 minus pi r. Okay, so that is said to be quadratic. Let's make it look a little bit more definitively quadratic. So I'll get pi r squared distributing, I'm sorry here, this x has been replaced. Okay, it's 2r x. Okay, distributing there would give me plus 3,000 r minus 2 pi r squared. Okay, I've got a r squared and r squared terms here, so this comes down to the a as a function of r being negative pi r squared, combining these two, plus 3,000 r. Of course, that is quadratic, 3,000 r. Okay, which means negative b over 2a, which means that going here is that negative b over 2a is negative 3,000 over negative 2 pi r. which, I'm sorry, not the r, just negative 2 pi, which brings this down to 1500 over pi. Now, what is the value of r for that value of x? This is the value of x. Optimizing the greatest area. I come back here, it says x is 1500 minus pi r. So x is 1500 minus pi r, okay, minus pi r. This is what r is, not x. This is what r is. So that's minus 1500 over pi times pi, which leaves x as 0. So oddly enough, to optimize this track, it'd have to be a circle. Not likely to be the shape, but mathematically that's how it works out. And that is your test.